4.4. Both lessons are on rational functions, so a new concept to a certain extent, talking about various properties, and then graphing for 4.4. Now, of course, I have to remind you, you have your exam, the first one, coming up. That's tomorrow. And it'll open up at midnight today, basically, right? So after the class, a few more hours at 12 a.m., it's going to open up, and it's going to be due at 11:59. Tomorrow, which is Wednesday. But again, it will not be available until midnight today. So hopefully that was explained and is pretty clear. And again, it's hopefully was explained over the past 2 weeks that it's two parts. One of them is MML. MML is the questions and the answers, where you would submit similar to your quiz. And Canvas is the work that you would submit as if you were writing these in class and on paper, how you would submit that work in person on paper. That's the same type of work that I'm expecting that you do during the online format and submit it by scanning it on Canvas. So the extra credit part for the practice exam, that is study guide. It is extra credit. If you chose not to do it, don't have to. I think it would be a good idea for a few reasons that I've talked about last week. One of them is the fact that you would practice the upload process, the scanning process, because if somebody's going to start their exam 10 p.m. tomorrow and, it's due in like 2 hours after you started, and you will run out of time, and then you won't have time to submit and scan everything. So if that's the case, I'm not going to be very lenient on that if you procrastinate till last minute. And that's why I'm encouraging that you should have done the study guide earlier, over the weekend preferably, and practice the upload method over the weekend. That way, if you had questions, you could have fixed it, asked me, and so forth. You wouldn't find the study guide on MML. I never said the study guide was on MML. It is on Canvas, and it's on Canvas. You would go to assignments, and that's where you will also upload the study guide. So it's kind of, again, this is not an online class. If you guys miss 10 minutes of me speaking about something during lecture, it doesn't mean you'll find it in the slides. I don't write everything down. I write most of it down, and I'm sure I wrote that the study guide is not on MML, but on Canvas. And I said and wrote a bunch of other things about the exam and the study guide, as well as when it's due. And if you look on your Canvas, you will see when it's due. And because I don't really like saying the same thing over and over, I will have you guys look on Canvas. So if you'll open your Canvas, and you will see study guide, you will see that the due date for it would be tomorrow at midnight, just like your exam. But if you haven't started your study guide, you still got some time, so you can still try and do it. And the answers are provided. So if you think that you're just going to kind of have the questions and the answers, then don't waste your time. I'm giving you the answers. I'm going to be looking if you did the work. But if you can find the time to do it, definitely do it. It'll help you on the exam. It'll give you extra credit, assuming you did it correctly, completely. and it will also help you with the practice of the upload process and the scanning process. Because if somebody does an exam tomorrow and they only do it on MML and they never send me anything on Canvas, that's a 0. I do have to see the work, because again, I'm trying to recreate essentially in-class environment where you have your papers, you do your work, you do your work, you do your work, you get to an answer, you're like, oh look, there's my answer, right? Answer goes, you underline it or box it up or highlight it, whatever you do. But you don't simply say, this is the question and then there's the answer and no work. You get 0 for that if you don't show any work. So this work stuff, all that, the work that you're uploading onto Canvas, including the boxed in answer that you probably, will put in your MML, but the answers do go into MML. Yeah, so I would prefer it's one file. I would definitely want it to be just one file, because if it'll be multiple files, I can still look at it. You can still upload them, but it takes you and me takes more time to get that done, because then I have to, you have to upload multiple files and I have to open multiple files for each page or whatever it may be. So make sure you guys have that all understood, because I've been talking about the test for starting, I guess, 2 weeks ago, I want to say, probably Thursday of last week, then Tuesday, and then Thursday of previous week, and now Tuesday again. We're talking a few last minute points about it, but hopefully this is all clear. Anything that you guys need me to clarify, anything you're still not sure about. It will be, it's not available now. If you look on MML, you won't see it, but in like 5 hours, it will be.
We have lecture on that date, right?
Tomorrow, no, we don't have classes on Wednesday usually.
Oh, so when you're talking about the MML answers, you're talking about the exam, not the study guide.
Correct. The study guide.
That's what I was asking about, the study guide.
No, study guide is only on Canvas. Study guide has no MML portion.
That's where I got a little confused.
I thought we were already talking about the exam. So study guide is all of it is on Canvas. You don't have to put in anything.
Thank you.
To MML. Yeah. And again, tomorrow is Wednesday, right? This is Wednesday the 23rd that we're talking about tomorrow, Wednesday, 23rd. We don't have lectures on Wednesdays, so there's not going to be a class tomorrow. But on the second exam, things will change, not drastically. I'm trying to slowly change them, but on the second exam, things will change, and I'll let you know when we get closer to that. For now, let's concentrate on the first exam. So somebody asked if you're doing a study guide and you're graphing circles, if you don't use the special tool, right, to graph circles, which I don't have here. I mean, I would just doing that for circles. I'm okay with that. Compass is the tool, right? If you have it, sure, but if you don't, it doesn't have to be super neat. And then, yeah, so that's fine. Anything else that we need to clarify prior to starting? Well, you guys will still have like the whole day tomorrow, and I will be definitely checking my messages tomorrow. So if you think of something, write me in Canvas, and I'll try to reply either tonight or tomorrow. So everybody, can get their questions answered. And yeah, I did push 4.1 and 4.2 back. I think I put it like Friday or Saturday. I don't always remember the dates. The exam doesn't include chapter 4, so 4.1 and 4.2 and whatever we're doing today, 4.3 and 4.4, those are not part of the exam. So the exam is only chapters 1, 2, and 3, whichever lessons we covered in there, right? So no for 1, no for 2. All right. Let's go ahead then and start the process here. And I think I need to get like one of those cooling pads for my tab, because by the end of the lecture it gets pretty hot and I think it starts to slow down. All right. So the first lesson is 4.3, which is rational functions. Rational functions. And first we'll define what is a rational function, what it looks like, and then we will talk about various properties that they have, kind of similar to how we did for polynomials. Right, we talked about what does it look like, the domain, some properties such as zeros, x-intercepts, multiplicities of those zeros, and behavior. But of course, rational function doesn't have the exact same properties, but some of them will be, you'll see that there's similarities. So we will define a rational function, r of x, to be in the form of p of x, this is a p, over q of x, where p of x and q of x are our old friends, polynomials. Polynomials. So if you have a polynomial in the numerator, you have a polynomial in the denominator, then that gives you a rational function. The domain for rational functions, because polynomials have domain all real numbers, but also because we have division here, and we know that q of x shouldn't equal to 0, otherwise we're dividing by 0, then our domain here is going to be all real numbers. And the notation for real numbers is this bold R, except x's for which the denominator q of x would be 0, right? So those x's we would have to exclude from the domain. And we've already done those examples in when we introduced functions and function notation and talked about domain. So it's exactly the same thing that we did for functions where we saw division, not the square root ones, because those wouldn't be polynomials, but where we just saw division. We just didn't call them rational functions back then. We would just treat them as a function. But now we're being more specific. So here's the domain, but we already know how to do that. Now, a little note that we have to put in: when you are in an algebra class, you talk about rational expressions, rational equations, and just like fractions, which we refer to as rational numbers, you do need to simplify rational functions to be able to do certain things with them. But finding the domain is not one of those things. So note, when looking for domain, do not reduce. Use the original function, use the original denominator. Do not reduce your function, otherwise you might lose a piece of your domain, which would translate into, when we start graphing these guys, into something called a hole. And yeah, so definitely we don't want to lose it. So let's do a couple here from the book. Let's say number 18. And if you're following along, these are from page 206 18 is defined as g of x equals 6 over x plus 3 times 4 minus x. Here, nothing would reduce anyway, so we don't have to really worry about that part. Again, we would say the domain is a set of all real numbers x such that, but then we have to see, well, what's got to be excluded from there. And what's got to be excluded is whatever would make my denominator equal to 0. Again, coming back to the definition of domain, domain are all values of x for which the function is defined as a real number. Here, we don't have to worry about complex numbers. There's no roots. But we do have to worry about division by 0, which is undefined. So that's where that comes from. And these, of course, we can solve. And get two values that we would need to exclude. One of them, x equals -3, so x cannot equal to -3. And the second one, x cannot equal to +4. So that would be my domain, and that's really it. Let's see if any of them are trickier in any way. Let's look at 25. So I don't think the study guide had chapter 4 in there from what I remember. I don't think I put any chapter 4 in there. So for 25, we have r of x equals 3 times x squared minus x minus 6 over 5 times x squared minus 4. And here also the directions, find the domain. That's all we're doing, nothing else. Now, for our domain purposes, I would not even bother factoring, reducing. I would just say, all right, let's see what our denominator is. This is my denominator. When does it equal to 0? And exclude those values. So again, if I reduce this, if I factored it, let's see, does it even reduce? If I factored it, this would be a x minus 3, x plus 2 up top, and it would be 5 and x minus 2, x plus 2 up here. And if I reduced it, this factor would go, right? It would be gone. And if I say that my domain, I only have to exclude one value, I would be wrong. The computer will mark it as wrong because you're missing out on that original function in which you would not be able to plug in two values. So that's why that note was there, to make sure that you guys work with the original form, the original denominator, and that way you would get two values. So the 5 doesn't do anything, right? Because we could just say, let's divide both sides by 5. We only worry about the non-zero factors. I mean, the factors that have a variable in there. And that would give me x equals 2, x equals -2 as what we would need to exclude from the domain. Where you see that if we reduced it, we would have lost on one of those values. We will still need to reduce it when we try to graph them, but not to find the domain. So here we're just discussing the domain. So this is the set of all x's such that x doesn't equal to +2 and doesn't equal to -2, like that. That would be my domain here. All right, so that's the domain part. That's one piece of information we're going to need, but we got a few more, quite a few more actually. This is not a short lesson. I will start with vertical asymptote next. So vertical asymptote And first, we're going to draw a picture. So if you have a graph, and at some point you have a vertical asymptote, what that means is your function cannot cross the vertical asymptote. And as it gets closer and closer to your vertical asymptote, function values get larger and larger. They go to positive infinity or perhaps negative infinity. Right? So it could happen that the function values either go positive or negative infinity. And actually, there's a few cases that are worth mentioning here, because when we find our asymptotes, you can see the process is similar to that of finding zeros, right? We would factor the denominator, we would treat that denominator as a polynomial, and then we would factor and try to solve and find those zeros. Well, but in this case, they're not zeros, they're actually asymptotes. But the multiplicity concept still stays here. So we will keep note of multiplicity if it comes from a factor that has an exponent that is the multiplicity. So if my exponent is 1 or there is no exponent, then multiplicity is 1 or odd. And same thing here, multiplicity is 1, or really we care if it's odd or even, right? Because that will help us with the graphing process. It's not going to be exactly the same as with zeros that we cross the asymptote or we bounce off of it. That doesn't really work here, but it does work as to where the function goes. So first, let's define the asymptote using some symbols and words, and then talk about multiplicity and how that works. So we're going to say if as x approaches c, and looking at my picture here, this is my x value of c, and I have a line, a vertical line, x equals c there. So as x approaches that value, function values approach infinity, or they could also approach negative infinity, but they get unbound. They forever go up or forever go down. So as we approach this asymptote on the x values, the function behaves in the following way. It either goes to infinity or to negative infinity, and it could differ depending on which side you're approaching from. The way that I have this picture drawn, for example, is as I approach c from the negative side, from the left side, that's the notation that we would use, the function values here are going to positive infinity. That's describing this guy here. As I approach c from the left side, that's what that little minus sign means. But as I approach c from the positive or from the right side, as I'm looking at what happens as I approach it here, well, the function values then are going to negative infinity on this picture. That's what I have. There are other cases. They could both be going to positive, they could both be going to negative, and so forth. But that's what that picture has. And that notation can be used, and it will be used a lot in calculus for sure. Not too much in pre-calc. So if as x approaches c, r of x approaches infinity, or r of x approaches negative infinity, then the vertical line x equals c is a vertical asymptote. Now, let's talk about what it means to be odd multiplicity and even multiplicity if we're talking about asymptotes. So if we have odd multiplicity, that means the following. So if there's my asymptote, one of the two things can happen. It's either doing that and that, but it's on different sides. So on the left, it could go to positive, on the right, it could go to negative, or vice versa. So I'll draw it next to it. On the left, it could go to negative, but on the right, it then has to go to positive. So it'll be on different sides of the x-axis. So it's kind of similar to odd multiplicity for zeros, because if we think about odd multiplicity for zeros, if you have a zero, it means we bounce off of it. So we change from negative to positive, or from positive to negative for multiplicity on zeros. On asymptotes, it still means that we change from positive to negative or negative to positive, but it's not connected, it's not continuous. It jumps from negative infinity to positive infinity, or vice versa. Whereas for even multiplicity, it stays on the same side, I guess we can say. Don't really like to say it because we're talking about infinity, but if one goes to positive infinity from one side approach, then the other would also go to positive infinity from the other side approach, if we have even multiplicity. Or they could both be negative. So if you have a vertical asymptote, they could both go negative infinity, but again, similar to zeros. For zeros, even multiplicity, we say we bounce off of that zero. So if we were negative, we'd stay negative. If we were positive, we'd stay positive. Here it's kind of similar. If we were negative infinity, we'd stay negative infinity on the other side, and vice versa. Positive would stay positive. So that's how we can use multiplicity for rational functions for vertical asymptotes. Any questions on that part? All right. Then we have something called the non-vertical asymptotes, as I will refer to them. Non-vertical asymptotes, and they're classified further. So the non-vertical asymptotes, we're going to talk about horizontal and oblique. And actually, oblique are classified even further. They could be linear and they could be nonlinear. So there's quite a few classifications there. The ones that we will concentrate on are horizontal and the linear oblique. You might get one example of a nonlinear oblique on your homework, if that, but they're not going to go into your tests or quizzes and such. So there will be 3 cases that we have to consider. But first, let's just in general talk about what it means to be a non-vertical asymptote. And actually, before I forget, let me get back to vertical asymptote and write something down here. An important note. Where would I stick it? I will move all of this down a bit. There, and I will add in the note here. Note. Function cannot keeps auto-correcting me. Cannot cross vertical asymptotes. because they're not part of the domain of your function. Anytime you exclude a value from your domain, that value may become either a hole in a function or a vertical asymptote, but it cannot have a value, so it cannot cross. The function cannot cross. To find vertical asymptote or multiple, to find vertical asymptotes, simplify. So for that part, you want to simplify your function, your rational function. If there is any common factors, you'd want to reduce them. And once it's simplified, set the denominator equal to 0. So if I were to scroll up a bit and look at our example that we had here, this guy, 25, the domain is correct, right? The domain is x everything except 2 and negative 2. But if I ask you to find the vertical asymptote, that's perhaps the later part. It would not be both of these values, because what we saw is that the factor of x plus 2 would cancel out, and the simplified version of g of x would now be this, 3 times x minus 3 over 5 times x minus 2. And I shouldn't use an arrow notation here. It would be equal to, with the exception that x should not equal to, because we had to exclude from the domain the factor that we had to cancel out. Negative 2 would have to be excluded here. But the vertical asymptote would come from setting the denominator of the simplified version equal to 0. So x equals 2 would be the vertical asymptote. So again, this is the later part. Since we already are at the later part, I can mention it here. So that's what I mean by first you would have to simplify, and then you would let the denominator equal to 0 to find this vertical asymptote. So this x equals 2 is a vertical asymptote. All right, now we are back to the non-vertical asymptotes, which we will classify as horizontal or oblique.
Professor, when we say the function can't cross the vertical asymptote, is that just because it wouldn't be an asymptote anymore, or is there more to it than that?
So, well, it's both, I guess. There is more to it than that, but it is in part because it wouldn't be it can't be an asymptote then. So just let's sidetrack, I guess, a little more here. So if I have an asymptote, this value, whatever it is, let's call it C, is excluded from my domain, right? My domain is everything except, and it could have other things in there, right? But one of them has to be this guy, right? It's excluded from my domain because of how I find the asymptote. So if it's excluded from my domain and somehow my function, who knows what it does, it crosses it and then gets closer and closer to it. Well, if it crossed it, it means my function is defined at that point. So that contradicts that it had to be removed from my domain. So it's contradictory to have an asymptote which cannot be in your domain, and at the same time have a function value at the asymptote, which is what it means to cross the asymptote, right? So that's why we can't have vertical asymptotes crossed. We can't have an intersection on our function with them. Does that make some sense, or?
Yeah, thank you.
All right. So this should not be happening, right? Can't cross vertical, but we can cross non-vertical. So we'll put that as our next note here. Function may, doesn't have to, but it may cross non-vertical. Asymptotes, whether they will be horizontal or oblique, that won't matter. It could cross them. May or may not, but it can. There's nothing wrong with that. It doesn't break any of the definitions or the rules. Now, when we talk about non-vertical asymptotes, we're talking about end behavior. So in that sense, there is some similarity to polynomials, right? For polynomials, we had end behavior. It wasn't very diverse. It was either positive infinity or negative infinity. That was it. For rational functions, there's a lot more options. First, let's define it with words. At least the horizontal asymptote. Let me think if I want to tweak the definition. Yeah, I'll try and tweak it a little bit. So let's do it like this. We'll say if as x approaches infinity or x approaches negative infinity. So this tells us we're talking about end behavior as x's go really large in the positive or in the negative direction. That's what that means. Our function r of x approaches, and we will use here this symbol L, I don't know, whatever we have. See, I'll just call it A, doesn't matter. So some number A. So this is one option. Then the line y equals A is a horizontal asymptote. But the other option is r of x approaches some other function. We will consider these examples where that function is linear, a line, but it could be a power function. So it approaches some other function, some polynomial, f of x. Then the graph of this y equals f of x is what's referred to as the oblique asymptote. But again, this is talking about end behavior as we go really large or really small. So in parentheses, we can say end behavior. Now, this tells us a couple of things. We can be approaching just, this is a horizontal line. Y equals some number is a horizontal line. So our function can get closer and closer and closer to a single value, and that's a horizontal asymptote. Or it can get closer and closer and mimic some other function. It could be linear, it could be quadratic actually, or any other polynomial. We will concentrate on the linear type. So as x's go to infinity, not only do we know that our function values will go to infinity or negative infinity, we will also know what it'll start looking like. For example, it can, if you have a slant asymptote, which is some line like that, then whatever my function does, at some point, it'll start getting closer and closer and closer to that line. It can actually cross it and then get closer and closer and closer to that line. So we don't really, well, we will be able to check if it crosses it, but it doesn't mean anything as far as the end behavior. and behavior talks about what happens all the way at positive and negative infinity, not what happens, close by. So again, we do have a note already here. Function may cross non-vertical asymptote. So that's fine. If you have horizontal or oblique asymptote, your function can cross them. And to check, actually, I guess I'll write that later. We don't need it right now. When we start graphing them, then I'll say how to check if it crosses it or not. So I'll move this. Now we will start looking at various cases of these asymptotes, non-vertical asymptotes. And before we write down any of the actual cases, let's try to remember a little bit from algebra. If I have r of x, a rational function, and it is of the form, as we said, p of x over q of x, there is a couple of options that can happen. What can happen is that the degree of your denominator, so if degree of the denominator is greater than the degree of the numerator, then we call r of x proper. Kind of like proper fractions. If you guys think back to the definition of proper fractions, if I gave you a fraction 3 over 7, this would be called proper fraction because the denominator is bigger than the numerator, so 7 doesn't go into 3. Versus if I wrote 7 over 3 or even 7 over 7, right? If it's less than or equal, then it's called improper, and we can change it to, for numbers, we call it mixed number. We could say, well, 3 goes into 7 2 times, and there would be a remainder of 1 over 3, which actually means 2 plus 1 over 3. So the process for going from this format to this format would be division. We're simply dividing. We can use mental division if it's numbers, or usually we would use long division if it's polynomials. So that is something that we're going to see. Now, the proper ones are the nice ones. The horizontal asymptote is easy for them to find. And before we write an actual theorem, let's just look at an example and see why that theorem would make sense. And then talk about the theorem. So if I gave you an example where r of x is proper, something like this, x squared minus 7x plus 3 over x cubed plus 2x squared minus 4x minus 12. Is this a proper rational function? That's a question for you guys. Is it a proper rational function?
Yes.
Yes, because we would say, well, what's the degree of the numerator?
3. I mean, numerator 2.
Numerator is 2. And then what's the degree of the denominator?
3.
3. So that's exactly what we have. Denominator is bigger. In degree, we're not comparing numbers anymore, right? We're comparing degrees. The denominator has a bigger degree, greater degree. Therefore, we would call this a proper rational function. And now let's think about its end behavior. So as x goes to infinity, what will happen with this guy? And we won't have to do it for all the cases. We will generalize this, but it gives us an insight as to why that's true. So this function r of x behaves in the following way. As x's grow really large or really small. So as x's go to positive or negative infinity, what happens with r of x? Let's think about it. Well, it's just made of two polynomials, right? And we know that the top polynomial will behave similar to its leading term, x squared. That's what we were doing for polynomials when we were discussing their end behavior. We would say, well, it's the leading term that kind of determines the end behavior. And the denominator polynomial will behave as x cubed. But we can reduce this. And anytime the degree on top is smaller, or we can say the degree on the bottom is bigger, you will have a leftover factor of x in the denominator. Or it could be multiple factors like x squared or so forth. But the numerator has a smaller degree, so those factors will be reduced, but there will still be leftover factors in the denominator if you have proper fraction or proper rational expression. But what happens with this 1 over x as x's go to infinity or to negative infinity? What does that approach? You can plug in some values. So if x is 10, what would be 1 over 10? Let's write it as decimal so we can see the pattern. So if I plug in x is 10, I get 1 over 10, right? That's 0.1. If I plug in 1,000, well, I get 1 over 1,000, 0.001, and so forth. So what does it seem that these are approaching as x's grow positive infinity or negative infinity?
Closer to 0.
It's going to get closer and closer and closer to 0, right? Because if I plug in, 1 with a bunch of zeros, well, this is 0.0000, right? A bunch of zeros, 1, very small. And infinity means it's unbound. It keeps increasing and increasing and increasing. So this approaches 0. And that's exactly what the theorem is going to say. That anytime you have a proper rational expression, the horizontal asymptote is y equals 0 because of what we discussed here. That there will be more factors of x left over in a denominator, and 1 over x or 2 over x or whatever is, any number over x as x goes to infinity will approach 0. My professors in calculus used to not like when I would write something like this, but if you say number over something very big, that's essentially going to 0. Doesn't equal, but goes to 0, right? Because if you have a number and you divide it by something big, well, it gets closer and closer to 0. But that's not very good notation, so I'm not going to write it. All right, so now the theorem for proper rational functions. We're just going to say if r of x is proper, then the horizontal asymptote is y equals 0. that's it. So again, proper, we have to remember what that means. Proper means degree on the bottom is bigger. And if that's the case, horizontal asymptote is 0. So if I gave you something like this and I said find the horizontal asymptote, r of x equals x to the 5th minus 7x cubed plus square root of 3x to the 2nd minus 12 over x to the 8 minus 9x cubed plus pi x minus, I don't know, square root of 3. Right, so these are still polynomials, therefore they're still rational expressions. There's nothing wrong with having coefficients that are not necessarily rational. As long as they're real numbers, we are okay. And if I wanted to find the horizontal asymptote, this would be very easy. I would just say, oh, look, the degree on the bottom is bigger than the degree on the top, because it's already in simplified form, right? If I had some parentheses in there, I'd need to kind of figure out, well, what is the degree? But it's pretty easy to see what the degree is. Degree on the bottom is 8, degree on top is 5. Therefore, this is proper. Horizontal asymptote y equals 0. And that's it. Are we okay? On the first case, that's probably the easiest case here. Or any questions on it? No, nothing. Everybody's okay. You guys hear me? Or
Yeah.
Yeah.
All right, just gotta make sure.
Yeah.
Till I force you to have your cameras on, I kind of never know, and that'll come soon. All right, let's consider the next case. In the end, I'll do like a quick summary as to what those cases are, but for now, let's just talk about each case individually. So we covered the proper case, right? The proper is the easy case, y equals 0. If it's improper, there are still few options there, right? Because if it's improper, one of the options is our degrees are exactly the same. So that's the next option for us to explore. So improper, rational function, degrees of numerator and denominator are equal, exactly the same. First, we'll again look at an example, and then we will kind of generalize the whole case, so we don't have to do the work every time. Excuse me. All right, r of x equals, let's say we have 5x squared minus 7x plus 9 over 3x squared minus 2x minus 11, something like that. Again, our goal is to figure out the end behavior. What does the function do as x values go to positive or negative infinities? And we will use kind of a similar, well, not really a similar approach, but we will say, let's change this into a different form. Let's divide, because, well, if we have an improper fraction, even if it's something like 5 over 5, I can still divide it, because my numerator is now at least as large as the denominator. Of course, for numbers, it's not very fun. If it's 5 over 5, you wouldn't get any remainder or anything like that. But for polynomials, if their degrees are equal, you can still divide. So we're going to change this r of x into a slightly different form, because anytime you have a rational function which is improper, and it's written in this way, we can do long division and we can find the quotient. Let's call it, let's call it f of x instead. So we can find the quotient f of x after we do long division, and then some sort of a remainder, right, divided by whatever the original divisor is. So I can change any improper rational function into this format just by doing long division. So that's what I'll do here. I'll do my long division. I'll do 5x squared minus 7x plus 9. I'll divide it by 3x squared minus 2x minus 11. Not the nicest numbers. I probably should reconsider. Let me change the 5 to a 6 just so I can make my point here, but I don't have to work with a ton of fractions. So I'm going to change this to a 6. And I then have to change this to a 6. So that way I'm not too worried about fractions. So 3x squared, and we only compare the leading terms when we do long division. How many times does 3x squared go into 6x squared? And that would be 2 times, right? Because we're basically saying what's 6x squared divided by 3x squared. In case you guys have forgotten some of your long division steps, you might need to review them. Then we would multiply, we would get 6x squared minus 4x and minus 22. We would need to subtract the whole thing, right? These would cancel. 6x squared minus 6x squared. Negative 7x plus 4x would give me negative 3x. 9 plus 22 would give me plus 31. And this guy is called the remainder, right? This is my remainder. So in my case, I can rewrite this function as the following. The quotient 2 plus the remainder, which is negative 3x plus 31, divided by the original divisor, 3x squared minus 2x minus 11. But this form helps me see something. Because now I say, well, as x goes to infinity, positive or negative, this here, because of the way long division works, has to be proper, right? The remainder, the degree of the remainder has to be less than the degree of what you're dividing by. Otherwise, you would just keep going with the process of long division until the degrees are no longer greater than or equal, but they're less than. Right? That's how long division works, until you can no longer go into. So this is proper. What do we know happens with proper rational expressions as x's go to infinity?
Goes to 0.
They go to 0. So this whole thing goes to 0. So our function will approach
2.
2. Now, what we notice is that we don't really have to do this whole complicated calculation every time. We notice that these are the only 2 numbers that actually play a role in all of this mess, right? When we were doing this calculation, we were just saying, well, how many times does this go into that? So we were basically just dividing the leading coefficients. And that's exactly how it's going to work, is just by dividing the leading coefficients that we can get the horizontal asymptote if the degrees are equal. So again, this only applies to the case where the degree of the numerator and the degree of the denominator is exactly the same. So let's write that as a little theorem now. We will use some language from polynomials that you guys hopefully remember. If the degree of numerator and denominator are equal, then the horizontal asymptote is the ratio. Ratio just means division of leading coefficients. So, do you guys remember what leading coefficients were in polynomials? Leading term, right? Leading term that has the largest exponent. From there, you can determine the degree of the polynomial, and the coefficient of such term is called the leading coefficient. So, leading coefficient in this case is 6 and 3, and their ratio is 2. So that's exactly how we would find the horizontal asymptote in such cases. We don't have to go through all of that complicated process. We can just do the following. If I gave you r of x equals 17x to the 5th minus 9x cubed plus 12 over, and this is a pretty weird looking 17. Let me see if I can fix it. Over, and then we will put, I don't know, 8x to the 5th plus 12x to the 4th minus 7x squared minus 9. And so we don't want to sit there and do long division on this, and we don't have to. If we're tasked to find the non-vertical asymptote for this guy, we would just observe that the degree in the numerator and the degree of the denominator, they're the same. They're both 5. So our conclusion would be y equals 17 over 8 is the horizontal asymptote. Does that make sense?
Yes.
Yes.
Cool. So any questions? Anything you guys want to clarify? All right. So these were the easier of the two examples. We have horizontal asymptotes. One is 0. The other is the ratio of leading coefficients. The last case is if it's greater, right? So first case was denominator is less. Denominator is greater than the numerator in degree. Second case, they were equal. So the third case is if the degree of the numerator is greater than the degree of the denominator. So if the degree of the numerator is greater than the degree of the denominator. Then we have an oblique asymptote. And the way that you would find the oblique asymptote is actually pretty similar to the process that we just did for finding a horizontal asymptote. It's not the same, but it is similar. So let's start based on an example, and then we try to generalize that. Let's say I have r of x equals, and the cases that we will see in our exercises in the book for the homework, on your quizzes, on your tests, is if it's greater by 1. So it could be greater by 2 or more, but we will just concentrate on degree being greater by 1. So if we have something like x squared minus 5x plus 2 over, say, x minus 3. Right, so here we have a case, degree in the numerator is 2, degree in the denominator is 1. So the numerator is the bigger one. So what we will have to do is we will have to rewrite it similar to what we did before. We will divide and rewrite it in this format where we can see what the quotient is after we divide and what the remainder is after we divide. So x squared minus 5x plus 2 is going to be divided by x minus 3. X goes into x squared. Now it's x times. When we multiply it in, x squared minus 3x, we would subtract. These would cancel. Negative 5x plus 3x, that's negative 2x. Bring down the plus 2. Now the degrees are the same, so we can keep going. We're not done. X goes into negative 2x, that's negative 2 times. Multiply that in. That's minus 2x plus 6. Subtract. Again, these will cancel. 2 minus 6 is negative 4. That's my remainder. That's my quotient. Right, so this is referred to as the quotient. This is the remainder. So if I write it in this form, then this is equal to, r of x is equal to x minus 2. And then you could do plus negative 4 or minus 4. That doesn't really matter over the original divisor, x minus 3. Now again, this is proper. This is proper, so where does it go? It goes to 0 as x goes to positive or negative infinity. This part goes to 0. All we're left with is this, and that is exactly the oblique. Some books also call it slant asymptote. I think slant refers to when it's linear, and oblique is more general. Oblique. So I'll just use oblique. So the asymptote would be x minus 2 because the other part goes to 0 and r of x approaches the line x minus 2 as x's grow unboundedly large or small, infinity or negative infinity. So no shortcut here. Don't have a shortcut. You got to do division, long division usually. Sometimes if you remember shortcut as far as synthetic division instead of long, you can do that. Doesn't always work, but that's how these are. All right, so let's go ahead and find some asymptotes. And let's see which numbers I like here. Let's do 48. Directions are to find all asymptotes, not just non-vertical, but all of them. Find vertical and non-vertical. Asymptotes. Now for 48, we are given a function g of x is x cubed plus 1 over x squared minus 5x minus 14. Now, we're not asked to find the domain here. If we had to find the domain, we would not simplify anything. We would just start with the denominator, set it equal to 0. But in this case, we are not asked with the domain question, just the asymptotes. For asymptotes, we do need to simplify if it simplifies. But in this case, even if I factor it, which my numerator is a formula from algebra that you might have forgotten for sum of cubes factorization, and the denominator factors as x minus 7x plus 2. So again, make sure you guys review factorization if need be. but nothing reduces, no common factors. So let's start with vertical asymptotes. Set the denominator of the simplified version to 0. This gives me x equals 7, x equals -2. These are exactly my vertical asymptotes. X equals 7, x equals -2. The non-vertical asymptotes, we would have to consider what the case is here. Non-vertical. Is it going to be horizontal or oblique based on my degrees here?
Oblique.
They will be oblique, right? Because
Oblique.
horizontals are only if the denominator is greater or if they're equal. Those are horizontals. But in this case, the numerator has a greater degree, so this will be oblique. And that means that in order to find it, we actually have to do long division here. No shortcut. Can't do synthetic division because we're dividing by quadratic. Synthetic only works if you're dividing by linear. So if I do my division, x cubed, I'll put in a bunch of zeros for the missing terms to make sure everything aligns. All of my terms are aligned. And I'm dividing by x squared minus 5x minus 14. And I start my process. And of course, my tab seems to be slowing down and down. So x here, multiply it in. That's x cubed minus 5x squared minus 14x. Subtract. Cancel, cancel. This becomes positive. This also becomes positive. Bring down the +1. Now we have +5. Multiply it in. That's 5x squared minus 25x. 5 times -14, that is -70 or something like that. But as you'll see, it won't really matter for this part. So when we subtract, these are gone. 14 plus 25, that is a 39x. This is a 71. But the asymptote is that, right? So my horizontal, or it's not horizontal, it's the oblique asymptote, is the line y equals x plus 5, right? That would be my actual answer here. That's the asymptote. I don't know if I actually did it on this example or if I just wrote it down. So my answer here was y equals x minus 2, the oblique asymptote. So that's how we find asymptotes. Let's see what we have. I'll give you guys one more example to try, and then we'll have to take a break, and I'll see if I can cool down my tab and get it normally operating again. Actually, we'll do 2 examples, but they'll both be pretty easy, I think. So we'll do 46. We have r of x equals 3x plus 5 over x minus 6. And 50. We have p of x here. P of x is equal to 4x squared over x cubed minus 1. Same directions, find all the asymptotes, vertical, non-vertical. Give you guys about 5 minutes to work on that.